Here are some questions with which you can check your understanding of the topics that you have learned till now. The first question is whether the given ODE is linear and separable. You can pause the video and try to answer this question. You must have realized that the ordinary differential equation given here, e raised to x y dash plus 3y is equal to x square y, is linear because y dash and y, the highest power of that appear here is 1. Also, y and y dash don't appear as a product. So this is a linear ODE. Also, you can suitably rearrange the terms and multiply with suitable factor so as to separate the variable x and y. So this is a separable ODE. The next question is whether the differential equation y dash plus 3x equal to 0 is linear and separable. Again, you can pause the video and try to answer this question. This equation is not linear because y and y dash appear here as a product. But this is a separable ODE because the variable y and x, you can separate it. This you can write it as y dy plus 3x dx equal to 0, and this is a separable ODE. The next question is the differential equation dx by dt is equal to, in the numerator, x plus 2xt plus cos t divided by 1 plus t square, linear or non-linear, and separable or not separable. You can pause the video and try to answer this question. Okay, so the given differential equation is linear because here the dependent variable x and its derivative, they are again appearing with maximum power 1. So here dx by dt is appearing, here x is appearing. You can rearrange so that the coefficient of x is 1 by 1 plus t square, the coefficient of t is 2x by, the coefficient of x is 2t by 1 plus t square, and then you have a function of x which is a function of t which is cos t divided by 1 plus t square. So this equation with dependent variable x and independent variable t is linear. Now whether it is separable or not. You can easily notice that this differential equation is not separable because you cannot separate the terms with variable x and the terms with variable t so as to arrange in the form of a separable ODE. The next question is, for the linear differential equation dy by dx plus x by 1 plus x times y is equal to 1 plus x, what is the integrating factor? You must be knowing what is the integrating factor from your previous knowledge. From your high school, you must have learned this. So this is a linear differential equation of first order, and to solve the linear differential equation of first order, we use integrating factors. We'll have some of those problems in the tutorial on solving first order linear differential equation. So you can pause the video and try to answer this question. must have attempted this question now. So you recall that the integrating factor is e raised to integration of px dx, where the differential equation is y dash plus pxy plus qx. So here you can see the px is x divided by 1 plus x. So the integrating factor will be e raised to integral of x divided by 1 plus x dx. You can simplify that expression and that will be your answer. And you can use this integrating factor to solve this first order linear differential equation. The next observation is the following. Note that for the differential equation, y dash square minus xy dash plus y is equal to 0, y is equal to cx minus c square is a general solution. What I mean is this y is equal to cx minus c square is a solution of this differential equation. You can verify it easily. You know how to verify that? You have to differentiate this equation. So when you differentiate, you get y dash is equal to c, and all this cancel. So you get y dash equal to c. So when you substitute c equal to y dash in this expression, you get y is equal to x times y dash minus y dash square. That is same as what is here. So this is a solution of the given differential equation. And since we have a parameter c which can be chosen according to our wish, this here the variables are x and y and c is constant parameter. So parameter c can be chosen according to our wish. So this is a general solution. But you may notice that y is equal to x square by 4 is also a solution of this differential equation. You can differentiate it. You get y dash is equal to 2x by 4, that is y dash is equal to x by 2. So when you substitute that in this equation, so here y dash is x by 2, so it will be x square by 4 minus x square by 2 and plus x square by 4. So this together will give you 0. So this is also a solution of the ordinary differential equation. But this solution cannot be obtained. Y is equal to x square by 4 solution cannot be obtained from the general solution y is equal to cx minus c square by choosing a suitable value for c. Such a solution is called a singular solution, a solution which cannot be obtained from the general solution. This I quoted to give you an example that there can exist solutions, singular solutions, which cannot be obtained from the general solution for certain differential equations. So many times people are of the impression that if you get the general solution, all the solutions are included in that. So that's not the case. And here is an example. Now, we'll discuss another class of ordinary differential equation for which we will discuss the method of solving them. This class may include the previous methods or previous class of equations for which we know the methods. For example, this class may include the separable ODEs. This class may include the homogeneous ODEs. But certainly there are ODEs in this class which do not belong to the previous class, and we'll learn a new technique of solving the ODEs here. So first order ordinary differential equation mxy plus nxy y dash is equal to 0 is said to be exact if there is a function u on two variables x and y such that del u by del x is equal to m and del u by del y is equal to n. So we are going to discuss about exact ODE. This kind of ODEs are called exact if such a function u exists whose partial derivative with respect to x is the function m and whose partial derivative with respect to y is the function n. Here is an example, or rather you can check whether this is an example. So the example that is given here is in bracket 2x plus y square plus 2xy dy by dx is equal to 0. Here your mxy is 2x plus y square and your nxy is 2xy. So question is whether the given ODE is exact or not. So you have to find a u whose partial derivative with respect to x is m and partial derivative with respect to y is n. At present we don't know any method, or I have not discussed with you any method of determining the u. So you can do it by observation, you can by inspection guess a u. So you can consider the function uxy is equal to x square plus xy square by guessing, and then find the partial derivative of this function with respect to x. The partial derivative of u with respect to x is 2x plus y square, which is same as what is appearing here, and the partial derivative of u with respect to y is this is 0 here, and this will be 2 times xy, which is precisely what is appearing here. So we conclude that the given ODE is exact. So such ODEs we learn how to solve them, how to get the solution. We recall some results from calculus. So given a function on two variables, namely u on x and y with continuous partial derivatives, we define its differential by du is equal to del u by del x times dx plus del u by del y times dy. So this is called as differential. We have learnt in a calculus course. And the function u is on two variable and it has continuous first partial derivative. Now if a ordinary differential equation mxy plus nxy y dash is equal to 0 is exact, then there exists such u on two variables xy such that del u by del x is m and del u by del y is n, that we have just now learned in the previous slide. So what happens is this ODE that is given to us and exact, we can write it in this form, namely 0 is equal to mxy dx plus nxy dy, and we know that this is exact, so we can replace mxy by del u by del x and nxy by del u by del y. So we get this expression, namely del u by del x dx plus del u by del y dy is equal to 0. But we know that this is the differential, so this means du is equal to 0, where du is shown here. But du is equal to 0, when we integrate, this will give us that u is constant. So this is a implicit solution of our exact ODE. That means if we can determine for our exact ODE the uxy, then just uxy is equal to c is the solution. But what are the steps involved? Is first of all to determine whether our given function is exact. If it is exact, then what is the u function that makes it exact, and then Once you get the u function, then you know the solution, namely uxy equal to c is the solution. So we'll discuss all these steps. So consider the differential equation, first order differential equation, in bracket 2x plus y square plus 2xy dy by dx equal to 0. So consider the function uxy is equal to x square plus xy square. You can see that the partial derivative with respect to x is your m for this equation, and partial derivative with respect to y is the n for this equation. Hence, the solution will be uxy equal to c, that is x square plus xy square is equal to c is the solution of the given ODE. Now, there is a working rule for us. Given any exact ordinary differential equation, namely mxy plus nxy y dash is equal to 0, the function uxy can be found either by inspection or by the following method. We have already seen how to determine uxy by inspection, provided the example is easy. But if it is not easy, then we follow a method. So what we do is the following. First of all, if it has to be exact, then we should be able to find a u such that del u by del x is mx. So you use this fact. So if del u by del x is equal to mxy, then we can integrate this expression with respect to x. What you will get is uxy is equal to integration of mxy plus a constant, but since this is a partial derivative and we are integrating with respect to x, so the constant k will be a function of y, so we'll write it k of y. It is constant with respect to x, but it is a function with respect to y because we are integrating only with respect to x. So ky is the constant of integration. Now we want to determine ky because integration of mxy is known, because mxy is known. If we determine ky, then we know the function uxy and then we know the solution. So how to determine kxy? So to determine kxy, we differentiate this given expression here with respect to y. So take the partial derivative of u with respect to y here. So this will be partial derivative del u by del y is equal to del of this expression integration mxy dx by del y plus k dash y, that is the derivative of ky with respect to y. Also, we know that del u by del y is nxy. So we replace this by nxy. So in this expression, we know what is nxy. We know the del by del y of integration of mxy because mxy is known. So because we know this quantity here and this quantity here, from that we determine what is k dash y, and once we know what is k dash y, we just integrate that and determine what is ky. And once we determine ky, we have in fact determined uxy, and so uxy equal to c is our solution. So this method we can use provided we know that the given differential equation is exact, but we are not able to guess what u will work for this exact ODE. By inspection, we are not able to find out. So we use this method to find out which u will work. Next, we will see a test to determine whether the given ordinary differential equation is exact. So if m and n and their first order partial derivative exist and they are continuous in a region D, which is a subset of R square, a region D in the xy plane, then we have the following two results. So we are going to see the proof of this also. So this is going to be test for whether the given differential equation is exact or not. So what is asked is the m and n in the differential equation, if their first order partial derivatives exist and are continuous on a region, then we have the following, namely if the ODE mxy dx nxy dy is equal to 0 is an exact differential equation, then my is equal to nx. The theorem states that if the given differential equation is an exact differential equation, then my, that is the partial derivative of m with respect to y, is always equal to the partial derivative of n with respect to x. The next statement says that the converse of this statement also holds when the region D is convex. What do you mean by region D is convex? The first region I am considering here is the region enclosed by this elliptical curve. The region enclosed here is convex, uh, is said to be convex when you pick any 2 points in this region arbitrarily and join those 2 points by a line, the line always lies in the region. In such case, we say that the region is convex. Now consider the next region, which is on the right hand side. Consider the region that is enclosed by this curve. In this curve, if we take in this region, if we take any 2 point, it is not always necessary that the line joining the 2 points lie inside the region. If we take any 2 points in this part, line joining will lie inside the enclosed region. But if you choose the point as shown here, the line joining is clearly lying outside, for some part of it lies outside the enclosed region. So this enclosed region is not convex. So this is what we mean by convex region. So here the claim is the converse holds provided the region is convex. If D is convex region in the xy plane, then if the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x, then always the ordinary differential equation is exact. The ordinary differential equation mxy dx plus nxy dy is equal to 0 is exact. Now in the problems that are going to encounter in this course, you will be always given a nice region which has no issue, which is always convex and nice enough. So the statement will hold in both the direction, namely if the differential equation is exact, then you can always say in those problems that my is equal to nx, and if my is equal to nx, then you can always conclude that the given differential equation is exact. So you don't have to worry much about whether the region is convex or not in all the problems that are going to encounter in this course. Now let us look at the proof, which is a short proof. So first we take the proof of the part 1. The given ODE is exact differential equation. In that case, we know that there exists a function u on two variable xy such that m is equal to del u by del x and n is equal to del u by del y. That is the definition of exact ordinary differential equation. Then we take the partial derivative of m with respect to y. So my is equal to del square u by del y del x. And we take the partial derivative of n with respect to x, that is nx is equal to del square u divided by del x del y. Now by the theorem on mixed partials, if we have this condition, the partial derivative exists and they are continuous on the region, then in this case, these two partial derivatives are equal. We know that del square u by del y del x and del square u by del x del y, they are equal. That is, you can interchange the order here, and so we conclude that my is equal to nx. So what is the conclusion here? If the given ODE is exact, then my is equal to nx. Conversely, if the region D is convex and you are given that my is equal to nx, then consider the vector field, namely a function h on xy valued onto R2, that is the plane, two-dimensional plane. So hxy is defined as the ordered pair where first entry is mxy, the second entry is nxy. Consider this vector field. So by our assumption, the h is continuously differential throughout the region. You recall that we have made some assumption here about the partial derivatives and its continuity. So from this assumption, it follows that h is continuously differentiable throughout the region D. So we compute the curl of h. We know that the curl of h, written like this, is given by this determinant ijk, then del by del x, del by del y, del by del z, mn and 0. So when we evaluate this determinant, what we get is nx minus my k, because rest of the terms here will come 0. So this is what we get. But what is given to us here? That my, it is given to us that my is equal to nx. So we get the curl of h to be 0. So we can use the result from our calculus that if the region D is convex, then curl free is a gradient function. So curl free is grade. So here we see the curl is 0, so that's curl free. So that means the h can be realized as gradient of some function phi. So h, there exists a phi on variable x and y such that the gradient of phi is h. So what is meant by the gradient of this phi? It means that it is gradient of phi is a ordered pair where the first entry is the partial derivative of phi with respect to x and the second entry is partial derivative of phi with respect to y. That means h can be written as partial derivative of x, partial derivative of phi with respect to x, comma, partial derivative of phi with respect to y. So if we equate this with the definition of h, what we get is phi of x is equal to m and phi of y. Phi x is equal to m and phi y is equal to n. So phi is precisely our u. So we have found a function u, namely the phi itself, whose partial derivative with respect to x is m and partial derivative with respect to y is n. So we conclude that our ordinary differential equation is exact. So we have proved the given theorem, and now this theorem can be used to determine whether the given differential equation is ODE. Now we have learned all the steps. So if we are given a first order differential equation, first order ODE, then first using this test, namely checking whether nx is equal to my, you can determine whether the given first order ODE is exact or not. And if you notice that it is exact, then we can apply the method of finding u either by inspection or by the rule that you learned in the previous slide. And once you find the u, then u equal to 0 is the solution. So we'll see some examples. So here is a differential equation: u cos x, y cos x plus 2x e raised to y bracket closed plus bracket sin x plus x square ey minus 1 bracket close y dash is equal to 0. So first what we have to do, we have to uh, check for this m and n whether it satisfies the test of exactness. So m here is y cos x plus 2x ey and n is sin x plus x square ey minus 1. So we test whether it is exact differential equation, and then we uh, find a u using the method that we have learned, uh, for which ux is equal to m and uy is equal to n. So first you can check whether the given differential equation is exact or not. You can pause the video and test yourself. So here, if you take the uh, function n and its partial derivative with respect to x, then what you get is cos x plus 2x e raised to y, and you have to take the partial derivative of m with respect to y, so you get cos x plus 2x ey. So you see that nx is equal to my. So it is an exact differential equation. So now the next step remains to determine the uxy. So we have learned that method that we can apply here. So what we do, we take the m, and since del u by del x is m, we integrate m with respect to x. So that will give you uxy is equal to integration of m. This is precisely the m that is given. So m is y cos x plus something. So it is y cos x plus this plus a constant which is actually a variable with respect to y. We can integrate this. The integration will be with respect to x. So it is y sin x plus, again integration with respect to x. So it is x square ey plus ky. Now we have to determine ky. So what we had done before is we differentiated this with respect to y. So when we differentiate this with respect to y, we get uy is equal to, differentiate with respect to y, we get sin x, and differentiate with respect to y, we get x square ey plus k dash y. And this is supposed to be equal to n that is given. So what is n given? N is sin x plus x square ey minus 1. So we equate this with n, which is sin x plus x square ey minus 1. So from this equations we get k dash y is equal to minus 1. So you can integrate this k dash ky, you can integrate this k dash y is equal to minus 1 to get ky is equal to minus y. We don't need the integration constant here, because anyway we are going to put an integration constant finally in the expression for u. So you got ky is equal to minus y. You substitute this in the equation here. So we get uxy is equal to y sin x plus x square ey, and in place of ky you write minus y. So that is ux, and this ux equal to c will give us an implicit solution. This clearly is implicit, and clearly at present the solution is not written as y is equal to some function of x, which will make it explicit. Now we recall some result for you. When implicit function form a expression or formal expression, we actually get an explicit solution. So if we have this implicit solution uxy is equal to c, this will define a unique differential function phi in the neighborhood of and passing through some point x0 y0 if u x0 y0 is equal to c, means we are taking a point in the neighborhood of the points where u takes the value c, that is x0 y0, and there the differential of u with respect to y, the del u by del y at that point x0 y0 should be not equal to 0. In that case, you can actually find in a small neighborhood of the point x0 y0 an expression of the solution y is equal to some phi of x. Here you can find an explicit solution. Well, this is general criterion. It is called implicit function theorem, but this is just for remark. You don't have to use this anywhere in this course. And this method fails to solve non-exact equations. What we said till now is that given a first order ODE, we check whether it is exact, and if it is exact, then we apply the method to determine the u function. But if we do the test for exactness and it may come out that it is not exact, then this method will not work. But still, one can solve such equations in many cases. So, for example, you just observe this particular ODE. Do the test for exactness. You can pause the video and try to do the test for exactness. What you have to do? You have to compute the nx and you have to compute my, and you have to see whether they are equal or not. So you'll observe that this equation is not exact, and so the method, you will see, it also does not work here. So for non-exact ODE, there is a way to solve. Certain non-exact ODE can be solved. So what we do is we multiply it by something called integrating factor, which makes the ODE into an exact ODE. So we'll learn that in our next lecture.